Hello everyone, this is a video covering the solutions to Homework 11, which is 8 problems from chapter 14. And I hope by the time we're done with this, you'll feel pretty confident handling problems related to the fluid mechanics. I think these problems cover basically everything I want you to know. So without further ado, let's get started. So the first problem is calculating the hydrostatic difference in blood pressure between your brain and your foot if you were 1.75 meters tall. So we can picture this as if it was just a tube of fluid which starts at a height of 1.75 meters and goes to a height of 0. And we want to calculate the pressure up here, which I'm going to call 1. The difference between the pressure here and the pressure here. So what we want is we want to calculate the difference in pressure, which is a difference of pressure 2 minus pressure 1, if you can remember that. At the beginning of this chapter, we had this equation that said P2 was equal to P1 minus rho GH, if you remember that. But it's actually probably more efficient just to remember Bernoulli's equation. And Bernoulli's equation says that the overall pressure, the total pressure at 1, so the total pressure at 1 is equal to the total pressure at 2. And the total pressure at 1 is the static pressure plus the pressure due to gravity plus the dynamic pressure, which looks a lot like kinetic energy. And the total pressure at 2 is the static pressure at 2 plus the gravitational pressure plus the dynamic pressure at 2. Okay? But we're going to assume that your artery or your vein or whatever that's running from your head to, or your brain to your foot, that it's got the same cross-sectional area at all points. And therefore, since we're assuming A1 is equal to A2, we have this continuity equation that says A1 V1 is equal to A2 V2. And if A1 and A2 are equal, then V1 and V2 are equal, and we can neglect these terms. So what we get is we get that P1 plus rho GH1 is equal to P2 plus rho GH2, where rho is the density of our blood, and G is 9.8 meters per second squared. Okay, so now that we've done this, we can actually find the difference in pressure, remember, is P2 minus P1. So if I move P1 over and I move rho GH2 over, I get that this is rho GH1 minus H2. And further, because I know that H2 is going to be 0 here, what I get is I really just get rho GH1, okay? Yeah, that's all well and good. Yeah, okay. So let's calculate what this is. So the difference in pressure, which is P2 minus P1, is equal to rho G H1 minus H2, and H2 we said was, H2 we said was 0, and H1 we said was positive 1.75. Okay, and so one thing that we can note here is that the pressure at 2 is equal to the pressure at 1, the original pressure, plus rho G H1, right? If we see that, that's because as we move down, this column of mass above us gets greater and greater. And that's what this term is. It's this gravitational force, kind of. But it's basically the amount of material above us pushing down, which is adding to the original pressure as the pressure of the brain. And from this, if we go back, the density of blood was 1.06 times 10 to the third, which is 1060. G is 9.8, and H1 we said was 1.75. This is delta P, and we get a change in pressure of 1060 times 9.81 times 1.75, or 18,179 pascals. I don't think this problem asks for it. I know the next one does, but let's turn this into atmospheres. In one atmosphere, there are 101,000 pascals, or 1.01 times 10 to the fifth pascals. So this, if I divide by, that gives me 0.18 atmospheres, which isn't too bad. I don't know. It's definitely significant, which is why if you hold your feet above your head, you actually kind of feel like you're, you can feel that pressure difference in your head. Your body's not used to that, but whatever. The main point here is that we used Bernoulli's equation to derive this equation, and that we didn't really care what P2 or P1 was. We just cared about their difference. That's what I wanted you to take away from this problem. The next problem is essentially the exact same thing. But what they're talking about here is that when you snorkel, if you have this snorkel and you imagine that these are your lungs, the pressure up here, there's a pressure down here on your lungs of P2. And that's going to push in on every part of your lungs, of your chest, of your body, or whatever, when you're down here. And the height too, they give us here. So they say when a person snorkels, lungs are connected directly to the atmosphere. The atmosphere, what is the change in pressure between the atmosphere up here and the water pressure down here? That's what they want to know, because that's the pressure that you're going to feel pushing on your lungs. So once again, following what we did last time, the change in pressure is going to be rho G, H1 minus H2. And so in this problem, what we really need to figure out is what is H1 and what is H2. And so if the length is actually down 26 meters or 26 centimeters, remember that this now, if we assume this is 0, then this is 0.26 meters, okay? We could also say that this was 0.26 and this was 0. Either way, we're going to get the same answer, because realize here this would be 0 minus 0.26, or we would have 0.26 minus 0. Either way, it's going to give us a positive 0.26. This is our H1 minus H2. Okay, and it's the same concept as before, that the pressure grows because this column of material increased by an amount P, or rho G H1 minus H2. So for the first part, we find that this is 1,000 kilograms meters cubed, 9.8 meters per second squared, and H1 minus H2 is 0.26 meters. That's not too bad. They want it in atmospheres, so we're going to have to multiply, turn it into atmospheres in a minute. But let me do this really fast. I get 2548, and 2548 pascals, if I turn it into atmospheres, divided by 1.01 times 10 to the fifth pascals gives me 0.25. Not too surprising. 0.025, I mean, atmospheres. Very small. Almost nothing. Almost no change in pressure. However, the problem then talks about an elephant. And an elephant being 12 feet high, or at least there's a difference of 12 feet between its trunk and its lungs, what would be the pressure there? And the only change we need to make is that H2 is now negative 4 meters. And therefore our delta P, or I mean our delta H, our H1 minus H2 is 0 minus a minus 4. So we get the change of pressure for the elephant is 1,000 times 9.8 times 4, and then we're going to put it into pascals, because the units here will end up being pascals. And what we'll get is we'll get 1,000 times 9.8 times 4 divided by 101,000, and I get 0.388. 0.388 atmospheres. As a total aside on this, that's pretty significant. If you were to go swimming in a swimming pool that was 12 feet deep, you would feel it on your ears, you would feel it on your chest. The water pushes on every part of your body with the pressure, and the pressure, even at just 4 meters, is pretty intense for a human being. It's why when divers go diving, they'll sometimes wear pressure suits that keep them, that help their chest from fight that pressure on them so that they can breathe. It's really important. Or wearing a diving suit that's pressurized, a pressurized suit to combat the pressure on the air, because at a certain pressure, the pressure on the water is going to be so great that your lungs can't inflate. And that's the point here. And it mentions that elephants have a membrane around their lungs that holds and protects the blood vessels so that they don't get squished and rupture. Okay, that's easy enough to understand. Basically, problems 1 and 2 are exactly the same. It's just determining the pressure change due to some change in height. All right, we're now moving on to Pascal's principle. And Pascal's principle said that you have something called a hydraulic lever. And if we have some enclosed vessel filled with incompressible fluid like water, water's definitely incompressible to a certain amount of pressure. And then let's say that this point and this point are able to move up and down. They're pistons that we can move up and down. So if we apply a force here, what will the force be here? Well, Pascal said that the pressure at 1, if it's enclosed and incompressible, has to be equal to the pressure at everywhere else, including where F2 is. Furthermore, we know that pressure is force over area. And since P1 and P2 are equal, this says that F1 over A1 is equal to F2 over A2. And what we want to know is if the piston diameters, so we're assuming they're round, and we're given the diameter of piston 1 and piston 2, if we know those, and we know what force we're applying here, what force do we get? So what this is saying is that the area of our piston will be pi d squared. And if we solve this for F2, then F1 times A2 over A1 is equal to F1 times pi d2 squared over pi d1 squared. The pi's will cancel, and what we get is F1. Now, d1 and d2 are both given in centimeters, so we don't have to change into meters unless you really wanted to. This is 49.4, and this is 4.05. I could either square them inside the parentheses, or I can square the ratio outside. Mathematically, it's the same. I get 49.4 divided by 4.05. And I multiply that by itself. The one problem that a lot of people have is they always forget to square that because we're talking about diameters here. We could have been given area, and then we wouldn't have to square it, but we're given the diameter. I get 148.78 multiplied by 33.1 kilonewtons. So this is 33.1 times 10 to the third newtons times 148.78. And that ends up being 33,100. I get basically 4925 kilonewtons. So I see that F2 is much, much, much greater than F1. And F2 is the force that's being applied at every point on piston 2. And that's the great thing about Pascal's principle is it's a hydraulic lever. You can apply a small force to a small area. And as long as you're doing that on an incompressible enclosed fluid, it has to go somewhere. And so at the output, you get the same ratio. So you can get a really big force if you make a really big area. That's good. I don't want you to think, I brought this up before, that that you're violating some physical law, because if we look at the work done, as we push down some D with this force on this small area, and then we push up with some D2 using this force 2, the work has to be the same. Whatever work we put in is the work that we get out, which means F1D1 is equal to F2D2. And we can see here, if we have a small force over a small distance, that's going to mean this very large force is going to be over an even smaller distance, right? In order for this to work. So, yeah, we can turn a small force into a big force, but we still just do the same amount of work. The nice thing, though, is that if you can use the forces in equilibrium to like hold something up, right? You can use the pressure to keep something from happening. And so basically you can use a small force to create a large force and then hold everything in equilibrium. Like, for example, the example shown in your book would be a small force 1 holding up the weight of a car, right? So some big mass weight here using fluid. It's kind of a cool concept. It works, again, because you have an incompressible fluid that's enclosed. It has to go somewhere. You're directing where it's going, and the pressure is being applied to every part. So you get the same amount of pressure that you put in when it comes out, which means that the area, if the area is larger, you get a larger force. That's a lot of words to say something that's very simple mathematically, and that's this. And the only problems to remember is sometimes the area is diameter and that the work done is always the same. So you might get a bigger force, but whatever work you do with force 1 is going to be equal to the work that you output. All right. The next two problems are essentially our quiz. And these are Archimedes. This is Archimedes' principle. And this, I need to remind you of a couple things, and we need to understand a few things mathematically here of what we're being told. So in this problem, we're told that we have a block, right? And this block is floating under the water. So we have some D and we have some H, and then block, the total height. So the volume of this block is going to be the area of whatever the face is underneath times H. But that is H plus D. That will come in handy a little later. I hope you understand this. So this is H plus D. whatever height above plus whatever height below is equal to the total height of our block. Now, Archimedes' principle says that there's something called a buoyant force that holds an object afloat in water that is equal to the mass of the water displaced, right, times g. But the mass of the water displaced is another way of saying rho times A times D, okay? Because that's how much of this volume is underwater, and we're using that this is true. So if we solve this, we get mass is density times volume, but the volume under the water, the volume of water that we have to take the place of is area times D. If we draw a free body diagram and assume that it's in equilibrium, we get a weight and we get a buoyant force. And the weight has to be equal to m times of the object times the volume, or times g, which is the density of the object times the volume of the object times g, which is the density of the object times A times h, right? The bottom area times the height. And this, we already said, was the density of the water times the area times d. And our acceleration, we can say is up, but it's 0. Okay? So writing Newton's equation, we get that ma is equal to 0 is equal to the buoyant force minus the weight, just from this, which says that the buoyant force is equal to the weight, which says that rho of the water times A times D is equal to rho of the object times A times H. But we're told that when it's in water, it floats so that 0.707 of its volume is submerged, okay? So 7.07 times V has to equal 7.07, hang on, is equal to D times A. But remember, this is A times essentially H is D times A, right? So getting rid of the A's, we see that D has to be equal to 7.07 times the maximum height. And from that, we can solve this. Let me go to the next page. I get that the density of the water, I forgot one thing here. And I don't mean to forget it. I forget it because it cancels out. We can see that we're going to cancel the A and the G and the A and the G. So we just get that the density of the water times D is equal to the density of the block or of the object. I'm going to put block because I'm going to use oil in a minute, times H, but D was 707 times H, okay? Therefore, the density of our block is going to be D over H, which is the density 707 H over H, or 707 times 1,000 kilograms per meter cubed, because this is water, such as 707 kilograms per meter cubed. Now, when the block is in oil, we get the same exact thing, except that our density is oil now, times D, is rho times the block times H. But when it's in oil, we see that it's 0.889 of the volume, which means that D is 0.889H. So here now, D is 0.889H. And we see that, I'm sorry, that O looks a lot like a B. So if we want to find the density of the oil, we see that this is the density of the block times H over 0.889H. And if we do that, this is 707 divided by 0.889, which is 707 divided by 0.889 is 795 kilogram meters cubed, right? Now, one thing that we should say is notice that this oil is less dense than the water. It's actually less dense than water. That's why the block actually sinks further in the oil than the water, because there's less density to that oil. It needs to displace more volume in order to match the density. I think that's pretty complicated for such an easy problem. And once you do a few of these, you can write down the solution, but to do the full analysis that we did here takes a little bit. But I really want you to understand how we got here. The quiz asks you to find H over D, which is similar to this, but vastly different. The mechanics are the same. What you're asked to find is totally different. In that, you substituted H plus D and found it. We're going to do that right now, actually. So here is an iceberg floating in salt water and an iceberg floating in fresh water. And what we want to know is what fraction of the volume of an iceberg would be visible, okay? So again, we're going to assume that this is some kind of cube, right? And we're going to assume that the iceberg has a height h, but below the surface is d, and above the surface is some value h, where h is equal to h plus d. And what we want is we want h over d. I'm sorry, we want the fraction of the volume. So we want h over h, not h over d. In this problem, we want h over h. The reason why this will give us the volume is we can see that if we multiply this by the area above over the area below, this is the volume that's visible over the total volume. And that's what they're asking for. So they're asking us for h over h. Now the buoyant force, and again, if ma is 0 because it's floating, then this is the buoyant force minus the weight. And the buoyant force in ocean water is the density of the ocean water times the area times d, the amount displaced, right? Times g. And the weight is the density of the iceberg times a times h times g. Setting the buoyant force equal to the weight, right, we see that the ocean water times a times d times g is equal to the ice times a times h times g. The a and g cancel, but I need to get h over big H. So I need d in terms of h and h. D is h minus h. And so what I see here is that I get the density of the ocean water times d is equal to the density of the iceberg times h. But the density of the ocean water is h minus h is equal to the density of the ice times h. If I collect terms, I see that I get the density of the ocean water minus the density of the iceberg times h is equal to the density of the ocean water times little h. And therefore, if I want h over h, that is density of the ocean water minus the density of the ice over the density of the ocean water, which is 1024 minus 917 divided 1024 minus 917 divided by 1024, and I get 0.1044. 0.1045 maybe. Okay, so about 10% of the iceberg is visible if it's in salt water. Because salt water has a higher density, it's going to float out. We can do this same analysis, exactly the same, for freshwater. And what we get is we get that H over H for freshwater is the density of freshwater minus the density of ice over the density of freshwater, which freshwater is 1,000 minus 917 over 1,000. And that gives us 0.083. Okay, so in freshwater, because the density is less in freshwater, the iceberg will float at a greater depth until basically the density equalizes. It's not too hard of a problem, a little bit of algebra to do. Mostly what I want you to take from this is knowing how to compute or how to find the equation of motion, where it's the density or the buoyancy minus the weight. In that quiz problem, I actually had for the third part, I added some mass, and I'll post some solution to that and show you that. But really, it's just adding another force of mg and solving for it, which isn't too hard. So Archimedes Principle is really about knowing what the buoyant force is, understanding that the buoyant force depends on the volume of the water displaced or liquid displaced if you are floating. And you don't have to be floating though. If it was going to sink, then MA would equal some negative amount, right? Or if MA was positive, it would be rising. So like an air bubble that's trapped under the water, right, could have an A that's positive because the buoyant force is greater than the weight of the air in this bubble. That's all I really have to say about that. Pretty easy stuff to do. All right, so we're now moving on, and we have, I believe, 3 questions left. This question actually looks like it's Bernoulli's equation question, but it's really not. This question is really about the continuity equation. In the continuity equation, the most important thing to remember is what it says is that the mass coming in and the mass leaving, so whatever mass comes in, the same mass has to leave because we're assuming this is incompressible and blah, 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 blah. And therefore, if I get a bigger area, right, then A1 V1 has to equal A2 V2. And what that's really saying is that if A2 is bigger because V2 is equal to A1 over A2 V1, if A2 is bigger than A1, then V2 slows down. And that needs to make physical sense to you. Basically, you have a wedge, but this wedge would be big. So this much has to pass every second. Only this little bit has to pass. So this delta x and this delta x is much smaller than this one. And therefore, this velocity is slower. Conversely, if you have a bigger area 1 and area 2, if A1 is bigger than area 2, then V2 is faster, okay? And this is the dynamic pressure. This actually changes. Remember that the dynamic pressure is rho V squared over 2. So when you have like your hose nozzle and you close it, you're increasing the dynamic pressure of the water leaving. You're not actually increasing the static pressure. In fact, the static pressure goes down as the dynamic pressure goes up. But what you're doing is by the continuity equation or the conservation of mass, passing each, or volume really, passing each point, you get this idea. And so what we have is that we have A1 V1 has to equal A2 V2. And in this problem, we have a hose with some original cross-sectional area. And then we have a sprinkler that has all these little holes, has 28 of them. And the water coming in here is going to leave all of these holes simultaneously. So basically A1, V1 has to be equal to, I'm going to call this big A, and you'll see why in a minute, V2. And big A is actually the sum of all the area 2's. And that's equal to the number of holes times the area of one hole, right? That's easy to understand, I think. Now the area of a hole has to be pi r squared, which is pi d squared over 4, right? So if we want to find V2, we're given V1, we're given the diameters of everything, and we're given the number n. So we have that V2 is A1 V1 over what I'm calling big A, which is pi times d1 squared over 4 divided by n d2 squared over 4 times velocity 1. I'm going to move to a new slide. So V2 is equal to d1 squared over d2 squared times n times V1. And if I go back here, notice that I've got 1.4 and 0.29. I don't need to change them to meters. 1.4 squared over 0.29, and there's 28 of them. 0.29 squared, and V1 is 0.094. Okay, so should V2 be faster or slower? Well, really, if we look at the area A1 is about 1.4 squared, that's 1.4 times 1.4, it's 1.96. And area 2 is this 28 times 0.29 squared. And this is 2.3555, let's say. So we can see here that this is actually going to make, since A2 is bigger than A1, V2 is going to decrease. What we get here is we get V2 is 1.96 over 2.35 times 0.94, or 1.96 divided by this answer times 0.94, and we get 0.782 meters per second. So this problem is really not so much about using the continuity equation. It's really about being able to figure out the area, to be honest with you. But you have to understand that this equation is true. And as you're going to see in the next two problems, we're always going to use this equation usually in Bernoulli's equation to find V1 or V2. That's why we need it. That's what it's for. So hopefully this isn't too hard and you understand. All right, so finally we're on to Bernoulli's equation. And Bernoulli's equation says that the total pressure at any one point is equal to the total pressure at any other point, assuming that this thing's enclosed and there's nothing weird going on. It's an ideal fluid, which means it's incompressible, irrotational, blah, 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 blah. And that gave us that the static pressure plus the gravitational pressure plus the dynamic pressure was equal to the static pressure plus the gravitational pressure plus the dynamic pressure. And so really all we have to ever do on these problems is we have to find P1, P2, H1, H2, V1, and V2, and we may need A1 and A2 to find V1 or V2 using the continuity equation. Okay? So this particular problem says that water is moving with a speed of 5.0 meters per second through a pipe with a cross-sectional area of 4.5 centimeters squared. The water gradually descends 12 meters as the pipe increases to 8 centimeters squared. So what this thing's doing is it's going like this, right? And we are assuming that A1 here and A2 here, and this is H1, and if we go down, this is H2, right? And that difference is 12 meters. So I'm going to say that H1 is 0, and I'm going to say H2 is minus 12 meters. We always have to assume that G is negative and down, therefore Y is positive and up. We could also say this is 12 and this is 0. It doesn't really matter. It's really up to you. But we're going to need to find V1 and V2. In fact, the first part of this, A, is what is V2. And then given pressure 1, we're going to have to find pressure 2. So we really just have to not worry about the pressure first. For part A, all we need to worry about is the continuity equation that says A1 V1 is equal to A2 V2. But V2 is A1 V1 over, I'm sorry, I'm changing my A's and I shouldn't be. All right. In this problem, we're told that the cross-sectional area is just 4.5 centimeters squared, and A2 is 8, so 4.5 and 8. So this is 4.5 centimeters squared, this is 8 centimeters squared, and it was initially moving at 5 meters per second. Now, that means it's going to decrease. We know that because area 2 is bigger than area 1. Turns out here that this is 4.5 times 5 divided by 8 is 2.8125. 8125 meters per second. And so we can go back to here, and now 2.8125, 5. We actually don't need these anymore. We needed them for the last part. Centimeters squared. H1 I said was 0, H2 I said was minus 12. I'm not given P2. In fact, part B wants me to find P2. This is 1.9 times 10 to the 5th pascals. Okay. And now, in order to find P2, looking at this, I can see that P2 is equal to P1. So P2 is equal to P1. Move this over and move this over. All right. So plus rho G H1 minus H2 plus rho V1 squared minus V2 squared all over 2. And then it's just plug and chug. Since I've got my variables, it's just plug and chug. So P2 is static pressure 1 plus the density of the water times G times the change in height from H2 to H1 or H1 to H2 plus the change in velocity squared from 1 to 2. And we know that this is H1 is 0 and H2 is minus 12, so this is 12. And we know that this is 5 squared minus 2.812, 5 squared. Density is 1,000 for water, and this was what, 1.9? So this is 1.9 times 10 to the 5th pascals plus 1,000 times 9.8 times 12 plus 1,000 divided by 2 times 25 minus 2.8125 times 2.8125 minus 7.91-ish. Okay, and what I get is I get 12 times 9.8 times 1,000 is 117,600. This is 190,000. This is 117,600, and this is 500 times 25 minus 7.91, which is 8,545. And if I add these all up, I get 117,600 plus 190,000. I get 316,145 pascals, which is like 3.15 atmospheres or something. Remember, you could divide that by 1.05 times 10 to the 5th pascals per atmosphere, and you could get atmospheres. Why did the total, or why did the static pressure at 2 increase? Because the dynamic pressure increased and the gravitational pressure increased, right? Since we're going down, there's more gravitational pressure on it, and because even though actually the dynamic pressure decreased. It decreased from P41 or rho V1 squared over 2 to rho times V2 squared over 2, and this decreased some, but this increased a lot more, so that the static pressure increased a whole bunch, because basically the pressure of gravity increased. You always have this tug and pull because energy conserved, and essentially this is the energy equation, remember? If we multiply through by the volume to every term here, we would get basically everything having units of Newton meters. And because of that, basically you're exchanging one energy for another, much like when we're exchanging potential energy of gravity for spring energy or kinetic energy, right? That's all we're doing. It looks different, but really that's what we're doing. We're exchanging static, gravitational, and dynamic pressures with each other. If one drops, another one should go up, okay? So the final question is basically that all over again. So let's review what we just did. We said that P2 plus rho g H2 plus rho over 2 V2 squared was equal to P1 plus rho g H1 plus rho over 2 V1 squared, and A1 B1 is equal to A2 B2. So the algorithm is write down your static pressure, write down your velocities, write down your heights, write down your areas. Right? And then start figuring stuff out. We're told that a water pipe having a 2.24 centimeter inside diameter. So we have this comes into the basement with some pressure and goes up to the second floor. So here we know that P1 is 187 times 10 to the third pascals. That's what we're told right here. And that its speed is 0.872, and that its area is what? Pi d1 squared, which is pi times 2.24. We can leave it as centimeters. We don't have to change it because we're going to use it in the continuity equation. So we know all that. We're told that it goes up. So let's say that H1 is 0, and we'll say that over here H2 is 6.03 meters. Okay? We don't know what V2 is. We don't know what P2 is. That's actually part B. But we do know that A2 is pi D2 squared, right? Over 4. I should say this is over 4. The reason why I'm dropping is we don't need to know any of that. All we need are the diameters. But this is pi over 4. It decreased to 1.58 centimeters. Okay? So, what do we know? We know that H1 is 0. We know that H2 is 6.03 meters. We know that V1 is 0.872 meters per second. I'm going to leave that alone for now. We know that the area is pi over 4 times 2.24 squared. And we know this area is pi over 4 times 1.58 squared. So we can find V2 from the continuity equation. That's A1 over A2 times V1. But A1 over A2 is just diameter 1 over diameter 2 squared. So this is just D1 over D2 squared times V1, which is 2.24 0.24 over 1.58, don't forget to square it, times 0.872. And if I do that, do not forget to square it. Turns out I get 1.753. This is actually almost a ratio of 2. Now that I have V1 and I have V2, this is incidentally the answer to part A, as before. It asked me what the pressure is at the second floor, and P2 is equal to P1, static pressure at 1, plus the change in height times the density times gravity, plus the density over 2 times V1 squared minus V2, or the change in dynamic pressure. Doing that, for 1, I like to write it like this and usually just do these parts separately. I don't know why, I just do. Remember that H1 we said was 0 and H2 was 6.03. So if this is 0 and this is 6.03, then this is going to be negative. So this is 1,000 times 9.8 times a negative 6.03. It actually lost gravitational pressure because it went further away from the center of the Earth. Remembering that this was 187 times 10 to the third pascals. That's the static pressure at 1. And this is 1,000 over 2 is 500. But V1 was 0.872. So 0.872 squared minus 1.753. And before we plug any numbers in here, notice something. As it went up, right, the area got smaller, meaning that V2 doubled, basically. V2 is double V1. So the water coming out at your shower, even though the pipe tapers to half the diameter, or whatever, I guess like 2/3 of the diameter, even though the pipe gets smaller, the volume or the velocity of the water actually increases. It doubles. But the static pressure goes down because you're losing gravitational pressure, and if you're gaining dynamic pressure, you lose static pressure. It's kind of that same give in energy. If you increase the dynamic pressure, you have to lose some static pressure or some gravitational pressure. It's a weird relationship, but we know that the dynamic pressure decreased because this is greater than this. So the dynamic pressure at 2 is greater than the dynamic pressure at 1. Therefore, the static pressure is going to have to go down. We see that because this is a negative and this is a negative. Let's see what these are. I'm going to write this as 187,000 plus 100 times 6.03 times 9.8 with a negative sign. So this is negative 5909.4. And this is also going to be a negative 0.872 times 0.872 minus 1.753 times 1.753, all times 500. And I get a minus 1156, which is very, very minor, right? I feel like that number is off. Hold on. 1,000 times 9.8 times 6.03 is 59094. Sorry, yeah, this part I messed up. And these are all pascals, right? They all have units of pascals. So this is, the pressure at 2 is 187,000 minus 59094 minus 1156. And that's 12 or 126750, which is still a little bit more than atmospheric pressure. But if you look, this was 187,000 pascals at the pipe where it was coming in. It decreased, right, by, what is that, 61,000 pascals. Most of that decrease in pressure was because we went up in height. We went higher up in the atmosphere, basically. And the other little chunk here is just this, due to this change in dynamic pressure. The dynamic pressure was greater leaving, so it lost some static pressure. It's all well and good, yay. But that's it. The main algorithm is just, like I said, finding your variables. The only other thing to take away from this is if this pipe was open to the air, or this was open to the atmosphere, you would say that this was 1 × 10⁵ pascals. So you might not be told that. And this little trick of your area having to be figured out from diameter, it's one of those Wiley plus things, really. But I wanted you to see it and get used to it. Pretty much, I hope after seeing all these problems, you realize that this is a lot of just plug and chug. There's not a lot of physics to do here. Not a lot of like free body diagrams or anything. The only major step is using the continuity equation to find the second velocity. Other than that, pretty fun, pretty easy. Maybe not fun, but easy. So I want to talk about, just real quick, I just want to rewrite these equations, these things that you need to know from chapter 14. And it's really that Bernoulli's equation. I guess I could start with force over area is pressure, and density is mass over volume. And volume is usually area times D or area times H or whatever. Bernoulli's equation says P1 plus rho G H1 plus rho B1 squared over 2 is equal to rho 2, or static pressure 2, rho G H2 dynamic pressure 2. And if the area doesn't change, these go away. So like a thermometer or whatever, or a barometer or whatever, you would just get that P1 plus rho G H1 is equal to P2 plus rho G H2. And really, that first equation in your book, the change in pressure is really P2 minus P1 is the change H1 minus H2. Incidentally, if you wrote delta H was H2 minus H1, then this would be minus rho G delta H, right? I think that's actually how they write it in your book, but it's fine. Yeah, so you have that. Pascal's equation says that the pressure is the same everywhere if it's enclosed and compressible. And remember that the work would be F1 D1 is F2 D2. And then what else did we have? We had the buoyancy equations. So Archimedes Principle says MA is FB minus weight, where FB is the mass of the water displaced times G, which is the density or fluid, times the volume times G, which is the density times the area times the depth that the object sinks in. The weight of an object is mg, which is the density of the object, I should say water, assuming it's water. Density of the object times the volume of the object, which is the density of the object times A times H times G. Right? And that the mass of an object is the volume of the object, which times the density of the object, which is the density of the object times A times H, right? And from there, if it's an equilibrium, floating A would be 0, but otherwise you could calculate by the force of buoyancy and the weight whether it rises or it sinks in a fluid. I think that's pretty much everything we learned. I hope I'm not forgetting anything. I guess I'm forgetting the continuity equation. A1 V1 is equal to A2 V2, where these are velocities. Keep in mind, these are velocities. This is volume. Down here, these are volumes, not velocities, right? Volume of water. Yeah, so it's nothing too crazy, too tough, I don't think. The last thing I want to say is I want to talk a little bit about the final. And our final is going to have 6 questions. It's how I normally do it. It will have a question on gravity, meaning it'll have some kind of Kepler's law or satellite in orbit or moving. It will have something to do with energy, and it will have something to do with elliptical orbits, much like the quiz problem or the homework problems. Go back and watch the video on homework 10 for that. It'll have a fluid problem, something from this homework, something from the quiz, most likely Bernoulli's equation. You'll have different pressures and different heights, and you'll have to figure something out. Not too bad. This would be pendulums. The newest lab and the newest homework has a couple of pendulum problems, but they're not very simple. And they're iffy. So just make sure you understand the physical pendulum equation, that the period is 2 pi, what was this? I over mgr, right? Go back and look at that lecture, just understanding that. There's not a whole lot to pendulums other than that equation. And then the last thing will be some oscillation equation. And oscillation problems are a lot like the, let me back up for a minute. The newest homework, the homework on chapter 15, the first 2 problems, you'll notice that homework is like double the points from a normal homework. The first 2 problems involve simulations of a pendulum and simulations of an oscillating block. And I think they're really good interactive problems on understanding how the energy works and the forces work on pendulums and on blocks. Then the first real problem is like this electric shaver. And we're going to have a quiz problem on an oscillation next week too. But an oscillation, essentially you need to find that equation, that x of t equation, which is x max, so the amplitude times cos, times omega t minus phi. You have to be able to find x max, omega, and phi, and then tell me what vt, at, whatever it is. So oscillations really aren't that hard either, as long as you understand how to read a problem and understand what these are. But you're going to get a practice final or 2 with solutions next week, or tomorrow, tomorrow. And you can look at how these problems work. I'm going to give them to you tomorrow in case you want to get studying on it ahead of time. But these 2 problems, these first 2 problems on the final, one of them is going to be like something we covered chapter basically 2 to 5, right? Or was it 6? 2 to 6. So basically exam 1, which means I've got to give you some kind of projectile motion or constant accel, or Newton's equations on a inclined plane, something like that. You'll have a problem that's something like that. And the second problem will be something from chapters 7 through 12. So equilibrium, right? Collisions, momentum, energy, right? Essentially though, those first 2 problems on our midterm, our second midterm, exam 2, really involve all those things, because you have torques and you have angular angular variables and stuff like that. And they involve understanding things on inclines, stuff like that. You'll see, basically it's, those first two problems are going to cover topics that we've already covered all semester. Drawing free body diagrams and figuring out accelerations for systems that are on inclines and pulleys, stuff like that. And the second problem will have some kind of collisions or energy, whatever, okay? So yeah, we'll talk more about that, but you'll see when you see the practice finals. If you're wondering how to study, that's what I would do. If you want to know what I recommend studying the practice finals and making sure you really know the homework on chapter 13, 14, and 15, and the quizzes. Basically, you understand how these problems work. The really nice thing about chapter 13, 14, and 15 is they all work the same way. Really, I've showed you all the tricky problems in the homework or in the lecture or in your quizzes. So as long as you know these problems, you're good. And I think you'll be fine. Anyway, as always, stay safe, be healthy, and I'll talk to you soon.